Cool. Okay, I guess we can go ahead and get started, and I'll just keep admitting people as they pop in. But first of all, good evening, everybody, if you're tuning in from the Arizona area. Thank all of you guys for joining up on our first online meeting for the Desert Data Science User Group. Again, this is our first online meeting, so we're going to see how it goes and maybe tweak it as we go along, but hopefully it's working out for everybody and everybody's able to access Teams okay. If you're having issues or you're stuck in the lobby, go ahead and just notify me in the chat or notify me wherever, and I'll make sure you get admitted. But I'll be paying attention to that as I talk, so pardon the delay. And if you guys have any suggestions, comments, etc., on how to run our future online meetings, feel free to just post those on the discussion board or on past events in the comments section on our meetup page. And yeah, just a couple announcements before I pass it over to Gowtham. Two things. First of all, there is actually an open source community day online event happening tomorrow, April 30th. My friend Enzo actually passed that along to me, who's also a big guy in the data science area in the Phoenix area. But it's basically just a kind of an online workshop day, kind of similar to if you've ever done SQL Saturdays. Very similar format. I can go ahead and link you guys in the chat as well as on the meetup page for that. But a lot of big companies are going to be there as well. Google, Microsoft, Amazon are all doing their own workshops. I saw there's a machine learning workshop as well. So if you're trying to stick exclusively to the data science related stuff, that's definitely going to be one to check out. Again, free to join. It's the Open Source Community Day, Open Source Community Day happening tomorrow. So feel free to check that out if you get the chance. The other thing is John Jordan actually forwarded over to me. He's running a data science newsletter called Overfit the Model, which is a great name for a newsletter. And he's mentioned that it includes job postings, articles, videos, etc., all related to data science. Hold on, let me admit. Oh, awesome, someone's got it. All related to different data science, again, postings, podcasts, all that good stuff. So if you're looking to get your fill of data science related materials delivered straight to your email, I'm going to go ahead and post the link to his online newsletter in the chat, and then I'll also be trying to get it plugged in on the meetup group as well. Before I pass it over to Gowtham, does anyone else have any announcements, anything of those natures, job postings that they want to share with everyone if they get the chance to unmute themselves? Now I see all the striked out microphones. I'm going to assume that means nobody's got anything to share at this time. I'll open it up at the end too if something pops up, and you can keep it in your pocket until after the presentation. But if we're good to go for now, then I'm going to pass it over to Gowtham, and it's all yours, man. Go for it.
Thank you, Jacob. Hello all. Thank you for joining on this presentation. I hope everyone can see my screen. Is that a yes or no?
Yep, we see your screen.
OK, thanks, David.
Yep, looks good.
OK, so I'll go ahead and start. So today I'll be presenting semi-supervised deep learning. A brief introduction about me. I'm a PhD student at Arizona State University. My hometown is Bangalore, India. My major is electrical engineering. My research is in two areas. One is distributed wireless sensor networks. The other one is deep learning. I've done previous internships in Lawrence Livermore National Labs, NXP Semiconductors, and this summer I'll be spending my internship at MathWorks. So in this presentation, what we can expect. So first, I'll introduce briefly about semi-supervised learning. Why do we care about semi-supervised learning and the motivation? In the next phase, I'll talk about different elements or the building blocks or some very important concepts that we need to know in order to construct different semi-supervised learning algorithms. I know semi-supervised learning is a very old topic, like it's been there from previous 2 or 3 decades, and there's a lot of work being done in this area. But in this presentation, I'll be covering the most recent ones, that is post 2015. So I'll be missing out on the classical machine learning based semi-supervised learning. And in the end, I'll be showing some of the observations and the recent state-of-the-art results in semi-supervised learning. So as most of us are familiar, deep learning is all about data-driven methods. So in order to build good models, we need lots and lots of data. So based on the amount of labels in the training data set, we can broadly classify this learning paradigm into three. One is unsupervised learning. On the other end, it is supervised learning. And when you have some portion of the dataset labeled, that comes under the semi-supervised learning regime. So in unsupervised learning, we mainly try to analyze the data, visualize it, and try to get some patterns out of it. So we mainly use principal component analysis, different clustering analysis methods, and in some cases, we also do anomaly detection, and we can build some generative models as well. VAE is a very good example. When it comes to the supervised learning, we have seen a significant number of applications in classification and regression problems. Like it is the bread and butter of many practitioners in deep learning. Apart from that, generative models are really cool to generate some cool images and for data augmentation. And there is also transfer learning and domain adaptation, which wherein you can transfer the knowledge that you learn from one domain onto the another domain. In this talk, I'll be talking about the semi-supervised learning. So something that is in this paradigm and it is related are graph-based learning techniques and few-shot learning and weak supervision learning. I'll not be covering these topics, but these are very closely related to the area. So most of us know the importance of collecting good quality data. So AI is not all about coding, but I can say with my experience, like half of the time I need to spend on preparing the data and half of the time I need to spend on implementation. And as we have seen in the previous decade, uh, with the resurgence of deep learning, it can be mainly attributed to the amount of data that we have right now and to the computational power. So one classical benchmark performance is the ImageNet accuracy. Like every major industrial company on deep learning tries to compete with their models on the ImageNet. So this is the most recent state-of-the-art models. So post 2018, we can see there are a bunch of papers reporting the ImageNet accuracy. By the way, ImageNet is a data set with 1,000 different classes with bunch of images for every class, and the goal is to classify them correctly. And now the state-of-the-art benchmark is at almost close to 88%. But the another important thing to notice is the where I have marked it in the red. All these algorithms use extra data set, like they go beyond the given training data set. They use images from Instagram and other media, and they build or they augment their training data set and get an improved performance. So this shows how much data is required and why is it so important. And when it actually comes to the data collection and labeling, it is a very tough task. So we have seen a lot of applications coming in the clinical area, and getting clinical data is really hard. For instance, like this was a recent paper on the COVID-19 on the COVID-19 case. Like this is a data collected from one patient. Like the first two images are the data that shows the progression, and third and fourth is the data after they start treatment to the patient. So getting this kind of data is very rare on the first case, and you need a domain expert to look through the data and to give you the labels. And it is very expensive for you to ask an radiologist to do this job, and it is time consuming as well. Not only in clinical applications, even when we go to the semiconductor industry. So what I observed is that, for example, in my previous internship, like we wanted to calibrate a lot of MEMS sensors. First of all, these MEMS sensors are very sensitive to the environment, and we need to collect their data. So usually we collect the data over a huge temperature sweep, like from minus 40 degrees Celsius to 125 degrees Celsius. So these sensors are placed in a temperature chamber, and it almost takes a day to collect so many measurements. And the amount of power invested to collect, at a time you can hardly collect data from 30 to 50 sensors, which is actually pretty less. So uh, uh, one can imagine, like, how hard it is to collect data and how expensive it is. And although now most of the algorithms are built around autonomous driving, so for that we need good object recognition models. And to create this data set, it is a huge and a tedious task. Like, you need to go through every frame of image, and you need to make a bounding box and label it. Even though now there are, like, Amazon labeling Turks which do the job for you, but even then it is still a painful process. So what does semi-supervised learning offer? So the whole idea behind semi-supervised learning is, okay, you have a limited data set which has labels, and there is a lot of unlabeled data out there. So can you leverage that unlabeled data along with your labeled data and improve the model's performance? This is just to illustrate the impact. So uh, when we take ResNet 50 and ResNext 101, which are standard architectures for ImageNet classification, without using any extra data apart from the labeling data set, their accuracy was like around 76 and 81%. But when they used the outside data like the Instagram images and other media images, they were able to bump up the performance by 5%. And 5% is a huge number when it comes to ImageNet performance. So this is not just an idea. So it has been shown that, using more data you can improve the performance. And similar one on the SVHN image SVHN classification task as well. As you increase the number of unlabeled data that you want to use, you can see a gradual reduction in the test error. And when I say the amount of unlabeled data, there are a lot of factors that come in, like whether these unlabeled data is from the same distribution or from the different distribution. So we don't have a good grasp on that particular part. And when I say 3.5 billion, not all the images pertain to the same class. So there will be like a filtering mechanism, which I'll discuss later. It's called pseudo-labeling. So it will take in only the relevant images into the pool. So that helps the learning process. So the other question is, like, will using or leveraging the unlabeled data will affect my decision boundary? So in order to explain this, I've taken a toy example. So this is called as a two-moon classification. So you can see if we follow my laser pointer. So this is one cluster and this is another cluster. And the ones marked with uh, cyan color is the labeled points. So if you build a classifier only using the labeled points, like I have used 3 different networks to do the task with different regularizers, you can see all the labeled data points are correctly classified. So if you check the training accuracy, it will be 100%. But if you see the decision boundary, there are some are like very highly complex and some are like, a linear decision boundaries. And you can see this bar. Green means the model is very confident about its decision, and blue means it is not so confident. It is like 50% is the worst for the two-class classification. So if you see, even in the wrong, not wrong region, you can see the models are very highly confident. But when I run the same algorithm, but I leverage the unlabeled data, I do a simple pseudo labeling, and if I use them, I'm able to get very good separation and very clear decision boundaries. So yes, using unlabeled data will definitely impact the decision boundary, and most of the time it makes your confidence boundary very smooth, and you come up with a better, robust, and generalized model. So that's why, leveraging more data will help you avoid overfitting the models. So in the past and in the recent literature, due to the lack of the right data set for semi-supervised learning, there have been some assumptions on the models that they built. So these are some of the assumptions, but these are not very. What I mean to say is the algorithms that I'll be showing next are scalable even beyond these assumptions. So the first assumption is label data that we have in the labeled data set is a very good representative of the data distribution. This is the common assumptions that most of the paper consider even in the supervised learning. The unlabeled data that we use is coming from the same distribution as the labeled data. However, the models can be built even without this assumption. The third assumption is that the data from all classes are almost balanced. Even this is an hard assumption, but there are models which go beyond this. A smooth cluster assumption, which is a common assumption that different clusters of data are have a smooth decision boundaries around them, and we want to build a decision boundary that goes through the low density region, which is the case in most of the times. Uh, uh, I would like to highlight some of the challenges when we work in this low label data regime. That the major challenge that we face are to avoid bias. So the decision that the model makes shouldn't be based on one or two features. And interpretability is always questioned and it is always challenged. Like, how can you interpret a decision of a model, mainly when it is a black box model? And scalability, like scalability comes into picture when you have lots and lots of data. Is it scalable for different data distribution, or when the data is coming from different domain? And robustness and generalization, like how good the data is. For example, if you feed an adversarial image. So for instance, I'll take data of white dogs and black cats, and I'll train my model. My task is to do cat versus dog classification, but when I feed in an image of a black dog and a white cat, what will my model predict? Mo- In most cases, it would predict the other way around because the model sees an easy feature of color and it uh, solely constructs its decision boundary on the color. Like I showed in the toy example, it takes the easier path. So this happens especially when you have very less data. So this is where the semi-supervised learning comes into picture. When you have lots of data, you build, you consider a lot of features into consideration, and your model won't be biased towards one or two features where you end up with incorrect labels. So before I talk about different semi-supervised learning algorithms, I want to go through different topics or different concepts that are essential part of those semi-supervised learning algorithms. Actually, you will be surprised to see, like, by combining two or three of these concepts, you can come up with a cool semi-supervised learning algorithm. So the first thing I'll discuss is consistency regularization, which involves data augmentation consistency, model noise consistency, and mix-up consistency. The next one is pseudo-labeling. Like I'll talk about both soft labeling and one-hot labeling. The other two components are entropy minimization and distribution alignment. So data augmentation is very crucial for semi-supervised learning. You always want to leverage the unlabeled data, and if possible, you can extend it. That is well and great. So the common data augmentation methods are, to do an affine transformation, to change the pixels, or to do a strong transformation on the image. Or this is a very cool technique, like using neural transformation, that is neural style transfer and adversarial noise. I have highlighted some of them in greenish and some of them in gray. This color represents a weak transformation and the gray represents a strong transformation. So you can imagine like, rotating an image, scaling or cropping, they are like weak transformation. But when you do a grayscale or image blending or adding an adversarial noise, where, it is very hard for the, it's a very hard transformation. So that comes under strong augmentation. So what is consistency regularization all about? So the main idea behind consistency regularization is we need to build a classifier such that it should output the same class distribution for an unlabeled image, and even when that unlabeled image is strongly or weakly augmented. So we see that uh, this improves the robustness and generalization. Uh, uh, what I mean is, let's say we have a model, and if I send an image X to the model, and I also send two corrupted versions with different noise, X plus noise 1 and X plus noise 2. If my model outputs the same output for all three images, that means my model is very consistent even with the data noise. This improves the robustness to noise and improves the generalization. So this category comes under the data noise consistency. And the other version is I have the same image, but I train different models with different noise. Like you can train a model with dropout. You can train a model by using stochastic depth, or if you are using ResNet, you can do skip connections. So there is some stochasticity in the model, but if the model learns to predict the same label, all the models learn to predict the same labels for the given image, then the model is learning the model noise consistency. And this is a very important concept, and this consistency regularization is being used in almost all the recent semi-supervised learning algorithms.
Quick question, Gautam.
Yeah, David?
Uh, in regard to the previous slide, I've seen the technique used where you run dropout on inference to
Yeah,
generate multiple uh, um, probability distribution of probable outputs.
correct.
Where would this map to in terms of these two examples?
That comes under model noise consistency.
Okay,
Yeah.
thank you.
So when we talk about the data augmentation consistency, the most important method is weak versus strong augmentation. So the goal is you want to build a classifier such that the weakly transformed image and the strongly transformed image get the same labels. For instance, the image that I have marked in the red block is the true image, and the image surrounding them are weakly and strongly augmented versions of the original image. So this is a pretty cool library, ImageAug in Python. So if you guys are interested in building computer vision models, I recommend this library. So this gives you some really cool transformations. So yeah, the goal is, you want the model to be consistent even with weak and strong augmentations. So the next class of consistency is Mixup. So Mixup is a very cool paper from Facebook AI research. So we can call it as an hack, but the concept is very simple and very easy to follow. Here it is mainly built on the principle of vicinal risk minimization rather than empirical risk minimization. So what do I mean by vicinal risk minimization? So in this technique, you generate additional samples by convexly combining two pairs of images and their labels. So let's say xi is one image and xj is one image. They could be from same class or different class. You create another image x tilde by doing a convex combination, that is lambda times xi plus 1 minus lambda times xj. You do the same for even the labels. So you get a new pair of data, that is x tilde and y tilde, and you can use this new pair to build your model. And in order to pick lambda, like lambda is random in nature, it is a random variable from a beta distribution. So you don't use the same lambda. And this lambda comes within 0 and 1, so you can easily combine them. So this is a very good illustration of how ERM works and how Mixup works, which is motivated from VRM. So orange is one class and green dots are another class. And blue is what is the probability that my class is orange. That is what the blue color represents. So you can see when we do empirical risk minimization, we always have a hard decision boundary and the confidence is very hard as well. So this region shows that the model is very clear and very confident in this region, and it is confident for the green region outside. But when we want a good generalization performance, we want a smooth uh, transition in the decision boundary. So when you train it with Mixup, because you are interpolating when you interpolate, you will be in this, the middle region, and your model will be learning the interpolated labels for them as well. So you get a smooth transition, and this is very important, especially for semi-supervised learning, where you have very less data and you don't want to overfit for that limited data. Recently, like there have been a lot of papers from Google, and everyone uses mix-up consistency in one way or the other in their paper. And we cannot leave out pseudo-labeling when we talk about semi-supervised learning. Pseudo-labeling is like the main ingredient of the algorithms. So the pipeline is that you take a model and first you train it over the labeled data set. So model learns some decision boundary. Now you want to generate some artificial labels for the unlabeled data. So you take the same model, which is trained over the labeled data set, and predict its output on the unlabeled data. We call that as pseudo labels or the artificial labels. For instance, if you have a 4-class classification, you take an unlabeled data and you predict, you might get something like this. So this is a soft label. It says, prominently, like it feels 60% confidence that this particular image belongs to this particular class. Uh, Now you can tweak this predicted distribution. You can do temperature scaling. That is, you can sharpen the temperature and you can make this much more a lower entropy. By lower entropy, I mean most of the mass is, projected towards one class. And some papers consider one-hot labeling. That is, they will take the argmax of the class. Like for example, for this, if you want to convert it to one-hot, you assign one where you have the maximum confidence and 0 to the other class. So you use pseudo labeling, to generate the labels for the unlabeled data. Now, once you have the labels for the unlabeled data, you can append both labeled data and unlabeled data. You shuffle them and you can train the model. And entropy minimization is actually a very good regularizer. Why we use entropy minimization is we don't want the classification decision boundary to pass through high density region. And we want the predictions of the model to have more mass over one distribution rather than having 2 or 3 different, like the bimodal distributions. One way to enforce that is to add the entropy term in the loss function. And entropy term is very simple. It is in the form x log x. That is, here h theta is the model h parameter by theta, and h theta of xi is the model's prediction for the data xi. So we use this term in the loss function to ensure that the model's prediction have a low entropy prediction. And this is another regularizer which is often used along with entropy minimization. These are like the implicit terms that we use in the loss function. So distribution alignment is important because one trivial solution that the model can say is it can find the easy minima where it can say, okay, all the data belongs to one particular class. So that will be a typical solution. So in order to avoid that, what we do is when we are training the model on the labeled data, we know the frequency of the true labels. So when the model predicts a class, we can compute the predicted class frequency, and we want to match the labeled class frequency, the true label frequency, and the predicted class frequency. So this is kind of a regularizing. So it makes sure that the model which is being trained on the labeled dataset is being anchored in a way to match. It is being anchored in the right direction, and we use the cable divergence term to match the distribution, and you can use this distribution element term in your loss function to improve the performance. And the most important metric in semi-supervised learning, according to me, is confirmation bias. So what is confirmation bias and why is it so important is the question. So confirmation bias comes into picture because we train a model on the labeled dataset and we completely trust the model to get predictions on the unlabeled dataset. And we know not all models are perfectly built and there will be some errors. So when you are transferring the knowledge that you learned on the labeled dataset to the unlabeled dataset, you induce some error while doing the predictions. And the models that we use in today's applications are so strong that it can even overfit that error. The error that we introduce is called as confirmation bias. And the goal to build a very good semi-supervised learning algorithm is to reduce the confirmation bias as minimal as possible. Even though we say that we can use dropout and other regularizers, the models can easily overfit this error, especially when we are using limited data. So in some literature, there has been some evidence that using mix-up and consistency regularization in semi-supervised learning algorithms can reduce confirmation bias to a certain extent. However, these are empirical studies. There is no concrete theory behind that. And this is still a black box on how to train the model such that the confirmation bias is reduced. So those are the some of the building blocks and key elements that were required to develop semi-supervised learning algorithms. In next couple of slides, I'll be going through the recent semi-supervised learning algorithms, mainly built for the computer vision applications. And these algorithms have been proposed almost like, post 2014 and 2015. So I'll go through these algorithms one by one, and I'll show the performance, like how algorithm fares on certain standard benchmark tasks. So the first basic algorithm is self-training. As the name suggests, there is a model and it trains itself by using the unlabeled data. So XL and YL is my label data. So YL is my labels. And I have only the unlabeled data XU. So now first step is I need to predict the labels for XU. Then I need to use this knowledge and train myself. So the classifier F is now first trained on the label data. It learns some decision boundary. Through this knowledge, we can predict the labels for the images coming from the unlabeled data. Now I can add this pair of data and the model's prediction, that is the images, to the labeled data. So my now I have augmented my labeled data. And now I train on this augmented data. Now my F is trained and I keep doing this process over and over again and I train the model. There are this was the basic algorithm and there is a lot of improvement done on this algorithm. Mainly every algorithm borrows the idea from self-training, but they use different modifications. So one basic modification could be I don't need to take all the data into consideration for the next iteration. I'll take only those image data and its labels which are highly confident, which why model feels very confident. This could be like, this could be these samples could be in the vicinity of the label data, which makes sense. So this is the basic self-training algorithm. Even though it doesn't do so well, the idea behind this is very intuitive. And the next algorithm which came in 2017 was Pi model. So in Pi model, they use both data and model consistency regularization method. So this is like, training an ensemble of the models and picking the label based on a voting mechanism. So this model relies on that. So let's look through the block diagram. So y is my label, a label of the image in the label dataset, and xi is my image. So I pass my xi to the model, where the model can be trained using dropout. So let's say we have two models. One model is working on one dropout ratio, and the other one is working on a different dropout ratio. Or this can also be done during the test time. Like you can train the model on one dropout ratio, and while doing inference, you can just replace the dropout ratio and do another inference. And even the data, you can pass the original data and through one network, and a transform data through the other network. So the goal is, you want the predicted image. Let's say we are passing an unaugmented data, that is zi. You want this zi to be correct. So you use the information from yi, minimize the cross entropy, which is the supervised loss, to make sure that your predictions are correct. So that is one term. The another term is, now you want the model to be consistent. So here you are inducing data consistency, data noise consistency, and you are inducing the model noise consistency. So with every inference, you get a different ZI distribution, and you want this, the labels for ZI and ZI tilde to be the same. So for that, you take the square difference between them. You can use different metrics like the KL divergence, and you form the final loss function. You can use a simple weighting, or you can do an adaptive weighting and build the algorithm. So this is the whole concept behind the pi model. Temporal ensembling is like an extension of the pi model. The only difference is, here you have a single network, and you get the consistency on the prediction distribution. So when you go to the next iteration, you take the difference between the ZI, the current version, and the ZI tilde, which is computed by taking a moving average on the previous predictions. So here this induces some kind of a consistency. So this is how the model learns the consistency, as well as to keep the model on track. We use the supervised loss. So these models were proposed in 2017. They achieved good numbers at that time, but there were other models proposed after that which significantly improved upon them. The further models that I discuss usually considers two models into picture. One is called as the teacher model, and the other one is called as the student model. Sorry. So the pipeline is very simple. First, what you do is, you take the teacher model and train it over the labeled dataset like we did in self-training. Then you take the teacher, predict its label on the unlabeled dataset. So you get the labels for XU. So you can, from the unlabeled data, now you can append both the labeled data and the unlabeled data. You can mix them, shuffle them, and you can train the student. So while training the student, you can add different components into your loss function. Cross entropy loss is a must because you want it to learn the actual labels. And you can use distribution alignment loss and entropy minimization loss to make sure that the teacher is not overfitting, as well as the student is also not overfitting. Now, once you do a single pass, you have a teacher and you have a student. Now, in order to go to the next generation of training, you swap them. That is, the old student becomes the new teacher. So now your teacher model is updated. Now you can retain the same student or bring in a new model as a new student, and you keep repeating this process over and over again. This kind of an iterative training has shown very good results, and this is one paper which illustrates why the teacher-student kind of a training works really well. And here the main mechanism is built on pseudo-labeling. That is, you are using teacher's knowledge to predict the labels on the student. But one missing component in this algorithm is how to avoid the confirmation bias. Here you are still trusting the teacher and its prediction to be true, and using that knowledge to train the student. And if there is an error induced due to trusting the teacher, that cannot be avoided further in the algorithm. However, distribution alignment and entropy minimization works to a certain extent, but you need to bring in the data consistency or the model consistency into your learning process to avoid the confirmation bias. Uh, the another work was mean teacher model. It was presented in 2017, and I mean, when you look at these semi-supervised learning algorithms, you will be surprised to see how similar they are from the previously proposed works. So in this, what they do is, unlike the temporal ensembling model, where they take an exponential moving average on the model's prediction, here they take the exponential moving average on the student model itself. So how they do that is, once you do an initial pass over the student and you have a student model ready, when you go for the next generation to build a teacher, the new teacher is nothing but the exponential moving average of previous students. So here they introduce that model consistency, and that's why they call it as a mean teacher, because it is exponentially moving average over previous students. And they show that using this technique, they can improve the performance, and their results are actually good. So all three algorithms, when compared to the recent algorithms, are above average and they do well. But the next couple of algorithms which I'll be talking, these are mostly from Google. They have, like, a huge gap between the performance with respect to the previous ones. And these algorithms, the next couple of algorithms are all from Google DeepMind, and they use data consistency regularization as common between them. How they use it is slightly different. Let's see one by one. So in unsupervised data augmentation, again, in this method, as you can see, we have a supervised loss and an unsupervised loss in your final loss function. Supervised loss is as the same. You take a model M, you feed in the label data, show it, you have the label for that data. So you can simply apply a cross entropy loss and learn the model. But in order to leverage the unsupervised data, what you do is take the unsupervised data and get the prediction for that unsupervised data on on the unlabeled data image. This image is not yet augmented. Now take the same image, perform augmentations. Here they don't differentiate between weak and strong augmentations. They apply a bunch of augmentation. So they get an augmented image and get the prediction of the model for the augmented image. Now this is the data noise consistency. So you want the prediction for this image to be same as the prediction for the augmented image. That is taken care by the unsupervised loss. As you can see here, the unsupervised loss is nothing but the KL divergence. There is a prediction distribution over here and there is a prediction distribution over here, and you want these two distributions to be as close as possible. And you add it to the final loss function, you definitely lead the supervised loss because you need to anchor in the right direction. But you can add this unsupervised loss as a regularizer, like you can use a lambda as a weighting function and you can train the model. And unsupervised data augmentation works really well. Um, and I have also shared the code for this. So you can use the GitHub link. It is an open source code if you want to try unsupervised data augmentation. So this algorithm is mainly built on the data noise consistency. And this algorithm also came during the same time as UDA. It is called a mix match. So a mix match, they cleverly use both data consistency, regularization, and entropy minimization. And more importantly, how they train the model is they use Mixup into the training process. Mixup was, it came like, hardly like an year before this. I'm not sure about the date. So they use Mixup, and Mixup does actually, it does wonder when we look into the results. So even in this method, there is a supervised loss and an unsupervised loss. Supervised loss is same as usual. P is the true target label, and you want the true target label to be as close as your model's prediction. So that has been taken care by supervised loss. And in the unsupervised loss, you have U. U is the unlabeled data, and your model's prediction for the unlabeled data should be close to Q. Now, here is where the novelty of this algorithm comes into picture. Like, how do you compute the label for the unlabeled data? So what this algorithm does is it takes an unlabeled data image. It does k different augmentations of the image. So you can see it's like an ensemble now. So the model will predict the labels on every augmentation. So you get a bunch of prediction distribution. Now you take an average. So here you are doing an average on the ensemble. Now this over this average, since we are taking an average, you don't usually expect a low entropy prediction, but you can use temperature sharpening to make it a low entropy prediction. And here is the term that you can use to change your average predicted distribution and make it sharpen. That is like, make it as close as possible to a one hot prediction. Now, this is nothing but your Q. So now once you know the Q, you can use it in the unsupervised loss term, and the model will now be able to uh, learn the model such that its prediction is more or less closer to the Q. So this is clearly a combination of data consistency regularization and entropy minimization. This comes in the entropy minimization is indirectly it is coming into picture because of the temperature sharpening. You are making the output low entropy. And this is the algorithm from the mixed match paper. I mean, even though it looks big, it is very simple to follow. I'll just briefly go over this. So X is your label data set with image XB and the labels PB, and U is the unlabeled data. Um, so what you do first is you take an augmentation on the labeled image, that is X cap of B. Now you need K different augmentations on the unlabeled data. So you do that here. You take K different augmentations, and on all the K different augmentations, you predict the model's output and you take an average. So there you get the average predictions over the K augmentations. Now you sharpen it. So now you end up with a Q. So now you can form the new data set that is augmented X and augmented and labeled U. Now you can shuffle them, concatenate them and make a single data set that is W. And here is the secret recipe of the algorithm. They use mix-up training, that is like, interpolating the two pairs and training the model. So this really helps the model to learn robust decision boundaries, and they have a very good improvement in the performance. So this is Mixup, and very in a very short period of time, like not even a couple of months, they released another paper called Remix Match. It is from the same a bunch of authors, and it's a very small extension if you see. So here they build the algorithm based on two components. First one is augmentation anchoring, and the second one is distribution alignment. Augmentation anchoring is nothing but weak versus strong data consistency regularization. What I mean is, you take an image, apply a weak transformation, and take a model prediction on the weak transformation. So that is here in the center highlighted by green. And then you take a bunch of strong augmentations, which is here, and it is highlighted by the blue response. Now you want to make sure that whatever the labels you predict for the weakly augmented image should be same as that of the strongly augmented image. That is what they term it as augmentation anchoring. Along with this, they also use distribution alignment. So like I spoke in the previous slide, distribution alignment ensures that your predicted class frequency will be the same as the true class frequency. So this distribution alignment works well if you are if your labeled data and unlabeled data is from the same class and from the same distribution, that is what the assumption they make in this paper, but you cannot leverage this when you have unlabeled data coming from a totally different class. So they use those two concepts and cleverly design their algorithm, and it works even better than the mix match. So the algorithm structure is very similar to the mix match. Even they have the same labeled data and unlabeled data setup. Here they bring in the concept of strong and weak augmentation, unlike mix match. So first, they prepare their data. That is, they take strong augmentation on the labeled data, strong augmentation on the unlabeled data for all the k different augmentations. Now they want to predict the label for this strongly augmented data. So for that, they take on the same data, they take a weak augmentation, predict the model's output on the weak augmentation, and apply the distribution alignment. So they get QB, which will be the label for differently strongly augmented K versions of the unlabeled data. And as usual, they have the strongly augmented original data with the labels. Now they form a unified set combining the unlabeled data and the labeled data. And like in Mixup, they use like in Mixmatch, sorry, they use Mixup training to build their model. And as you can see, they use different elements in their algorithm. They use the Mixup consistency, they use the weak versus strong augmentation consistency, and they also use the regularization by using the distribution alignment. So this paper is again from the same authors. They released it in succession, and this was the state of the art for at least quite some time. So here again, they use consistency regularization, which has been a common recipe in all the previous algorithms, and they use one-hot pseudo-labeling. So this is where their novelty comes into picture. And it is so cool that you can cleverly combine 2 or 3 elements and come up with an algorithm and make it work. So here we can see they take an unlabeled image, unlabeled halls, they apply a weak transformation and a strong transformation like they did in remix match. But here, once they apply the weak transformation, they take uh, they take the one hot representation. That is, if and only if the module produces a highly confident output, they convert that output into a strong or one hot label and use this one hot label to train the strongly augmented unlabeled image. So in the previous image, they were using soft labeling, but here they go on to the hard labeling. And even though it might seem as a very small increment, but the model does really well. And I'll show you in the experimental results like how strong these numbers are. And this algorithm is very simple. Like in the previous algorithms, they have the supervised loss term as well as the unsupervised loss term. In the supervised loss term is straightforward. You minimize the cross entropy of the model's prediction over the alpha is the weakly transformed image and PB is the original target. So the supervised loss term makes sure that your algorithm is moving in the right direction and learning the actual labels. But now in order to leverage the unlabeled data, here you are using a masking mechanism, that is thresholding and converting it to one hot. So in order to do that, you take a strong transformation on the unlabeled image, and you want this prediction to be as close as is your QB, where QB is your prediction on the same image, but it is weakly transformed. So here you can see the data augmentation consistency, and you simply weight it like ls plus lambda u lu, where lu is the weighting factor, hyperparameter again, and you train your model and it works really well. So this is fixed match. So, and then came this cool algorithm, Meta-Pseudo Labels in 2020. All the previous algorithm missed one part. That is, their training process was happening in one direction. Teacher learns on the labeled data and the student transfers or distills the knowledge from the teacher. But teacher was never getting a feedback from the student like how well the student is doing, or can the teacher update itself in a different way such that the next student might improve the performance? So this part was missing from the previous algorithms. And in this algorithm, they address that. So in this, the idea is to build a teacher such that it can adjust its target distribution so that the student can use this and improve the performance. Uh, this is the block diagram. I'll quickly go over the block diagram and say what is happening here. So here, training data here is nothing but the unlabeled data, and the validation data is nothing but the labeled data. So you train the teacher on the validation data, that is the labeled data for certain epochs. It need not be completely trained. Once you are in that process, you do an inference on the teacher. That is, you take the predictions of the unlabeled data and you get the pseudo labels. Now you have the pseudo labeled data, that is the unlabeled data and the predictions of the teacher. And this is like in the previous algorithms, you train the student on the pseudo labeled data. So the distillation process of the student is the same like in the previous algorithms, but what changes is how you update the teacher. Now, as we see, student hasn't seen the label data. In the previous algorithms, we used to concatenate both the label data and the unlabeled data and train the student. Here, student is purely trained on the unlabeled data and it doesn't see the label data at all. Now, since it hasn't seen the label data, you can evaluate how well the student is doing because you know the labels. So you can evaluate, for instance, you can compute the cross entropy loss and see how well the student is doing on the unseen labeled data. Now, the goal for the teacher is to update such that students does very well on the validation on the validation data. Now, this is a different kind of an update. So there is a paper called as model agnostic meta learning, which where they leverage the idea from that paper, and it is a meta learning update. So meta learning is a huge topic, and it will take an entire lecture to talk about meta learning. It is a very cool idea, and uh, you should be aware of that. I mean, there are bunch of papers in that area, but you can leverage that idea to update your teacher. So this is where the secret recipe of this algorithm lies in. And this algorithm has some surprising results. So why MPL works? Like, what is the intuition behind it? Why does it actually work? Here, teacher observes the student performance on the held out validation set, and it learns to generate a target distribution so that if the student learns from such distributions, the student will achieve good validation performance. So it is doing so by achieving good validation performance on the labeled data set, which it hasn't been seen, even though it is a less in number, that gives you a kind of a metric to evaluate how well your student is doing. Even in this method, there is a missing element. That is, in all the previous algorithms, there is nothing to enforce that the model will do well on the unlabeled data set. And the reason why it is very hard to enforce is because we don't have the labels for the unlabeled data set. And if we take the labels from the teacher, there will be confirmation bias in it, so you can't completely trust the labels. So I'll quickly go through the update equations. So student model is parameterized by theta, and how it updates is the simple gradient descent step by taking the gradient over the cross entropy loss function between its output and the predictions of the teacher. Teacher is q of phi, q model q parameterized by psi. Now the most important update is on the teacher, because in this method the algorithm depends on the teacher. If the teacher does well, the student will plainly distill the knowledge from teacher, and it does well as well. So in order to update the teacher, you need to take the gradient on the cross entropy loss of the student's performance on the validation data set, which is quite different from what we have seen before. So now this is a reward signal for the teacher, and the teacher has to update itself such that it will improve the reward. By improve, I mean to minimize the loss function. So if you differentiate this loss function, you see that it is a gradient over the gradient. So that is where the meta learning comes into picture. So this differentiation requires computing gradient over gradient, which is performed by meta update on the teacher. And to make sure that MPL is not just label correction, like it is just not correcting the labels, we can see the results of this algorithm. So if it was label correction, we would have expected the teacher to go to 99 or 100% accuracy because the label dataset is so small to reach to overfit the label data, and then the student to distill that knowledge. But here, since the teacher is actually predicting the target distribution for the student, you can see how the training process is going on. So in another words, the teacher model is MPL is enforcing the student to prevent overfitting on the label data, which is very crucial for the semi-supervised learning scenario. Those were some of the recent algorithms right from 2015 to 2020, which were proposed for semi-supervised learning, mainly for the computer vision tasks. Now we see what are the common tasks that these papers consider and how they evaluate different algorithms. So there are three main computer vision tasks. One is CIFAR 10 image classification. So CIFAR 10 is a dataset with 50,000 images, labeled images in the training set, where there are 5,000 images per class and there are a total of 10 classes. It is an RGB image classification, and CIFAR 100 is a much more harder problem wherein you have 100 different classes and less labeled data. So you have 500 labeled data per class and you have 100 classes. And SVHN is a complex dataset wherein even it is an RGB. You have 10 classes where each class represents an individual digit, and here it is not like uniform as CIFAR datasets. It is imbalanced, and the amount of imbalance is not that bad as well. So now the goal is to use only 400 images per class when we have 5,000 in the original dataset, and to reach the same performance. So in the CIFAR 100 case, it is like 40 images per class, and in SVHN, it is only 100 images per class. So these number amounts to less than 10% of the dataset. Like you are using only 10% labeling, and you want to achieve the same performance as if you had 100% labels. So I would like to start with an obvious observation, like what happens if you increase the number of labeled data points. And it is quite obvious, like when you are giving it more labeled information, you expect the test error to decrease. So that is what we see even on CIFAR 10 and SVHN. In this slide, I'll show you the main result of the fixed match paper. When the fixed match paper came out, the MPL wasn't yet published. So fixed match was the state of the art during that time. And they evaluate their performance against all the previous methods which we discussed: the pi model, pseudo-labeling, mean teacher, mix match, UDA, remix match, and fixed match. So as you can see, the amount of experiments that they do in this paper are really great. So they do CIFAR 10 classification using only 40 labels, 250 labels, and 4,000 labels, which is like less than 10%, and this is almost like using only 1% labels. And as a baseline, when all these models are trained over a wide ResNet, they keep the network to be common in all the papers to have a fair comparison. And the fully supervised result on the wide ResNet is, if I'm not wrong, it is close to 3% error. So when you're using only 10%, you are achieving an error rate of 4.3 or 4.2, which is close to, you're coming close to the fully supervised performance within a percentage difference. That is actually very great. And even on CIFAR 100, which is a much harder problem, with 400 labels, as you can expect, like there are only 4 labels per class. So you have classification error of about 40%. The worst case scenario is like, if it predicts the same label for all the classes, you still be at 90% error. So 40% is actually a good number. But when you increase the number of labels, like if you take 100 labels per class as opposed to 500 per class, like when you utilize the 20% labeling, you get an error performance of 22%. When we go to SVHN is much simpler than the CIFAR because you don't need the complex features, it's just the digits. So here you can see the error rate is just 2.5%. When you're using only 100 images per class, like that is less than 5% of the images. So these were very strong results from the fixed match paper. And recently this year, when the Meta-Pseudo Labels paper came out, it completely outdid the fixed match results. So here MPL along with the unsupervised data augmentation, it reached a whopping 96.11% accuracy, and 97 is the accuracy when you are using full all the labels on wide ResNet. So it is very close, even within a percentage. So this is a great result. So this shows like how semi-supervised learning algorithms can be so effective. So using only 4,000 labels, that is 400 images per class, as opposed to available 5,000 images per class, you are reaching an accuracy of 96%. That shows like, how important the different concepts that we saw, like the data augmentation consistency, the mix-up consistency, and the pseudo labeling techniques that you use are effective. And they also uh, check their scalability performance of their algorithm on ImageNet. ImageNet is a significantly harder task. Like you are dealing with 1,000 class classification, and even with all the label data on that particular network, the maximum accuracy that you can reach with all the label data is 76.9, and only by using 10% of the labels, UDA and MPL together was able to achieve like 74%. It came like within 3% of the fully supervision performance. So this is actually a very good number. And this result is pretty obvious what we expect. Even on the ImageNet data, as you increase the amount of labeled data, you can see how gradually the performance of the algorithms increase. Yeah, so the algorithms which we saw are pretty easy and pretty cool, and you might expect you can implement it very easily, but the hard fact is these algorithms are very sensitive to the hyperparameters. There are a bunch of hyperparameters in every algorithm, and when you look at the ablation studies, even for a minute difference, like even for a 0.1 or a 0.05 difference in certain hyperparameters, you blow up the performance by 3 to 4%, which is significantly huge. So that is one tough part, while training these algorithms. And these models usually take on a general GPU, they take at least a day for these models to train, and that makes these training the models really hard. So I covered work that had been done past 2015 and majorly focused into the computer vision algorithm side. But there are a lot of other works in the literature, like there are a bunch of papers on graph-based semi-supervised learning. So I would recommend you all to take a look at them as well. And recently there has been like this area has been the hot area, like few short semi-supervised learning. Like they use as less as like 3-4 labeled images every class, and they design few short algorithms. I couldn't explain few short algorithms because they need a separate treatment, and I couldn't do justice if I had added the few short learning into this presentation. And semi-supervised learning is not only limited to computer vision algorithms. There has been a lot of work even in natural language processing. That is when you have the time series data. So if anyone is interested in natural language processing, I highly recommend this paper by Yoshua Benjo. So it is a very good paper which shows like how semi-supervised learning methods can be leveraged even in NLP. And more importantly, when we talk about semi-supervised learning, If we also associate it with transfer learning and domain adaptation. That is, in a way to think is, what if my unlabeled data is not from the same distribution, but I'm getting my unlabeled data even from the other distribution? Yes, you can use pseudo labeling or one-hot labeling. You can check the model's confidence and add those data into your pool. That is one way to combat that. But are there other algorithms which effectively use the out of distribution samples without doing a transfer learning kind of a framework? There are like in the literature, when I looked in, there are like 1 or 2 papers, and a lot of interest is shown in this area, like how to use the out of distribution samples. So this is something that I couldn't cover in this presentation. So I'd like to wrap up. We saw quite a good number of semi-supervised learning algorithms. We saw how these algorithms are constructed, and that's it. So if you guys have any questions, I'm open to questions.
Thanks, Gowtham. Well done.
Yeah, thank you.
I'm clapping now.
That's fine. Yeah. That was a lot of different algorithms, but the essence that I wanted to say is that how to construct a semi-supervised learning algorithm and how to leverage the unlabeled data.
Gowtham, is there any way we could make this slide set available on the meetup group, or maybe like a different version of the slide set if you're using this for private research purposes?
No, I can hand over the slides to you, so that's fine. I'll
Awesome.
send it to you, yeah, so you can share it with the meetup group.
Perfect. I was thinking some people might want to go back and look at some of these algorithms in more depth or have them in front of their screen at some point. So that would be
Sure.
perfect.
Yeah, sure.
Cool. Anyone else for questions for Gowtham? Otherwise, I'll go ahead and start wrapping things up. Any takers? No. Microphones look like they're on mute. So cool. I guess we'll wrap things up. Again, thank you guys so much for tuning in to our first online meeting. If you guys had any comments about stuff you wanted to adjust, or any ideas for our next meeting, it looks like this is how we'll be doing meetings for the foreseeable future until we hear otherwise. So stay tuned for that. But otherwise, as always, we'll be hosting this meeting on YouTube for the recording if you want to check out some points Gowtham made earlier. And it sounds like we'll be able to get the slide deck if you guys want to look at those algorithms in more depth. Just a couple of reminders for those of you guys who came in late. For events going on, we got the Open Source Community Day happening online tomorrow. I believe it's free to attend that online workshop event. A bunch of different companies are going to be presenting different workshops there, including Google, Microsoft, Amazon. The link for that is in the chat, as well as the data science newsletter run by John Jordan, overfitthemodel.com, also in the chat, and I'll be adding those to the meetup group, or excuse me, yeah, to the meetup group as well. So that way you guys are able to access those as you want to. But if that's all we've got, thank you guys again one last time for joining in, and we'll see you guys in a month.
Thank you, Jacob. Thank you, Jacob, for arranging. Yeah.
Awesome. Thank you again, Gowtham, for that great presentation. Very thorough. It was awesome.
Yeah.
Thank you, guys.
Thank you.